Hey everyone, it's Mr. Lau. Last time we were together, we talked about London dispersion forces and how they are necessary if you want to form what I would call a molecular liquid. You want molecules to stick together in the liquid phase, you have to have London dispersion forces. If you need to, go back and watch the last video. You can see exactly what they are. Now, in this video, we're going to try to see what kind of impact these London dispersion forces can have. I have a table on this page that looks at all of the different diatomic molecules, our Brinkelhoff elements, if you will, and looks specifically at one property, the boiling point of each one of these molecules. And what you'll notice is that you have quite a variety in terms of the boiling points. I2 iodine has a boiling point of 457 Kelvin. That's pretty high. And if you look down at hydrogen, it boils at 20 Kelvin. That's just above absolute zero. So it's pretty easy to boil hydrogen, but pretty tough to boil iodine. Why boiling point? Why boiling for that matter? I want to go back a couple of slides just for a moment to look at what it actually means to boil a substance. We know that that phase transition going from a liquid to the gas phase is what boiling actually is. And it's going to happen at a variety of temperatures depending on the properties of the substance itself. The thing that you'll notice is that to go from the right side to the left side in this picture, all you have to do is really separate the molecules from one another. So, what does that entail? Well, it means breaking apart those London dispersion forces that we talked about in the last video. So, literally, all you have to do if you want to boil a substance is break these London dispersion forces in between each of the molecules. And that's going to take a different amount of energy depending on how strong the London dispersion forces are. For fluorine, it happens at 85 Kelvin, so kind of mid range amongst all of the diatomics that we had on our list. But if I go back, what that means is it's much, much harder to break the intermolecular forces, the London dispersion forces in iodine, than it is in something like hydrogen. Well, why is that? Well, I think the best clue is over in the right-hand column. Look at the total number of electrons for each one of these molecules. It seems to be directly proportional to the boiling point. So in other words, the more electrons present in a molecule, the higher the boiling point. Well, what does that mean? It means that the London dispersion forces are stronger when we have more electrons, and they're weaker when we have fewer electrons. It's easier to break apart molecules from one another if there are few electrons for the London dispersion forces. It's much, much harder if you have a bigger molecule with more electrons in it. Now, I also included molar mass because sometimes scientists will substitute molar mass for the total number of electrons. Just something that we're more used to calculating, and there's a direct relationship between the number of electrons in the molecule and the molar mass. So something that has a great deal or a huge number of electrons is also going to have a pretty large molar mass. Now, I graphed all of these boiling points versus the molar mass of each compound. This is something that you're going to do in an exercise in just a few minutes. What you'll notice is that again, if I look at let's set up the axes first. On the left hand side or on the y-axis, I have boiling point. Those are in Kelvin scale temperature. And on the x-axis, I have molar mass. That's in grams per mole. And I've just plotted boiling point versus the molar mass. And the heaviest molecule, I2, is way up there in the right-hand corner. it has the highest boiling point. That makes sense. And the lightest of all of the molecules, H2, has the lowest boiling point. That makes sense. In fact, the trend is pretty stable. What I would say is there's one little disruption to the trend. If you look right here between O2 and F2, those two molecules seem to be a little bit off. Let me go back just for a second and look at the actual data. If you look at O2, it is lighter and has fewer electrons than F2, but it has a higher boiling point. That's for another video. That's a discussion we're going to have in our next video, actually. But otherwise, the heavier the molecule is, the greater the strength of the London dispersion forces, the harder it is to break apart those molecules from one another. And therefore, to break them apart, you have to have a greater amount of energy or a higher temperature. So they boil at higher temperatures when they're heavy, and they boil at low temperatures when they're light. If you take a look at the next data table, I have a group of molecules called the alkanes. These are hydrocarbons. They just contain carbon and hydrogen, and they're all very simple nonpolar molecules, straight chain hydrocarbons. What you'll notice is the smallest one, which is CH4 up here in the left-hand corner, has the lowest boiling point amongst those alkanes, and that the heaviest one on this list, which is called hexane, has the highest boiling point on the list. So we're going to take a break here, and we're going to do a little bit of a graphing exercise. So if you would, pause the video or the video's finished, go back to our Google Meet, and I'm going to explain exactly what I would like you to graph. When we come back to another video, we'll try to explain the difference between O2 and F2 and why there's a discrepancy compared to the general trend. See you in just a moment.